Hello, this is Dr. Lukes, and this is your video lesson for Friday, September 14th. We're going to be looking at an example problem. In class on Wednesday, I distributed a handout that has this problem statement, and I'm going to ask you to kind of work along and pause the video and try working it on your own, and then come back and see what it is I've done. So let's look at this problem statement. Now in this case, we have a sphere of iodine that is 1 centimeter in diameter, is placed in air at 40 degrees C and 747 millimeters of mercury. And this air is moving at 10 centimeters per second past the sphere. Now at this temperature, the vapor pressure of iodine is about 1.03 millimeters of mercury. And for the sake of estimating diffusivity, this diffusion volume that we're going to need for SO2 can be approximated as, well, the diffusion volume of iodine can be approximated as that of SO2. And then we have some data, and unfortunately my formatting got lost when I brought it into my app here. So the viscosity is 1.93 times 10 to the minus 4th kilograms per meter per second. The density is 1.113 kilograms per cubic meter. The molecular weight of air is 27, and the molecular weight of iodine is 127. And a gas constant that is convenient in this case is R equals 82.06 atmospheres times centimeter cubed per mole Kelvin. And the first thing I want you to do is estimate the diffusivity in centimeters squared per second of iodine into air. So this is saying that iodine is component A and air is component B. So this is the molecular weight of B. This is the molecular weight of A. And pause the video and go work on this. Okay, so if you've done this correctly, then you know that we need to, for gases, use the equation that is on page 425 of your book. And this is the formula for diffusivity. Now, if you look in the tables in the book, noting that if A is iodine, and we can use the diffusion volume of SO2, then V sub A is going to be 20.1, and for air, V sub B will be 41.1. So I'm going to plug these in. The T needs to be in Kelvin, so this is 313 Kelvin. M sub A is 127, M sub B is 27, VA and VB I found over here from the tables. The pressure is 747 millimeters of mercury, and in this formula it is supposed to be in atmospheres. So 747 millimeters of mercury divided by 760 puts this into atmospheres. So if I plugged those values in, what I found was the diffusivity of iodine into air is approximately 1.32 times 10 to the minus 5th meters squared per second. Or we could say 0.132 centimeters squared per second. Okay, so we found the diffusivity. The next piece of this is I've asked you to find the Reynolds number. Now in this case, I want you to use D as the characteristic length. So that is an assumption. But for a sphere That seems the most reasonable assumption. Okay. So again, pause the video and come back and let's look at that answer. All right. So in this case, the Reynolds number is the diameter times the velocity times the density divided by the viscosity. This is my viscosity, my density. The diameter is 1 centimeter. Since these are in meters, this is 0.01 meter. And my velocity is 0.1 meters per second. So 0.01 meter, just 1, not a 0, 0.1 meter per second, 1.113 kilograms per cubic meter, and the viscosity is 1.93 times 10 to the minus 4th kilograms per meter per second. Okay, kilograms are canceling, per seconds are canceling. Meters, I have a per meter in the denominator, so that means it's like on top in the numerator. So I have 1, 2, 3 of them that will cancel with these 3. So this is dimensionless. Always be sure you are verifying that this answer comes out as a dimensionless quantity. And I found that the Reynolds number is 5.77. All right, so what's the next piece of this? Next, I asked you to find the Schmidt number. Again, pause and come back when you think you've got this solved. The Schmidt number is viscosity divided by density times the diffusivity. Now we found diffusivity just a few moments ago, so we'll use that estimate. And again, this is one of those things that should be a dimensionless quantity. So be sure that you check on dimensionless quantities that they really do all cancel the units. In this case, I want to use the form that is in meters squared per second so that I have my units cancel. This plus this cancels with this. And my Schmidt number is 13.1. Okay, next. Look for the Sherwood number. Now in this case, the Sherwood number is 2 plus 0. And the formatting is terrible. Okay, so that's what this chunk here is saying. So 2 plus this piece over here. And since we just found the Reynolds number and the Schmidt number, use those to find the Sherwood number. All right, the Sherwood number is 2 plus 0.552 times 5.77 to the 1/2 power times 13.1 to the 1/3 power, giving us an answer of 5.13. Now, with all of these values, we can estimate Kc prime. Now, again, we're saying that d is the characteristic length because in a sphere, that's the value that makes sense. So pause and see if you can figure out what Kc prime is. All right, Kc prime, I'm going to use the definition of the Sherwood number. The Sherwood number is Kc prime times the diameter or characteristic length divided by the diffusivity. So if I'm solving for Kc prime, I'm going to use the Sherwood number times the diffusivity over the diameter or characteristic length. And in this case, I'm going to take my answer from a moment ago. 5.13. My diffusivity. Now this time I chose to work with it in centimeters squared per second because I could use D in centimeters. And in this case, I get 0.677 centimeters per second. Now that's Kc prime. And that's what I could use to figure out the flux if my units are in concentration units. But what if I want K sub G? Again, pause. You're probably going to need to look up some formulas in your book. Pause and come back when you think you've got the answer. All right, in this case, K sub G relates to Kc prime using the log mean partial pressure and the total concentration. Or if total concentration in a gas can be estimated using the ideal gas law, I have this. Now, this partial pressure of B log mean is going to be the differences in pressures divided by the log of the ratio of the two pressures. Now I have worked this using units of atmospheres. Okay, so this is my vapor pressure of iodine taken from the pressure that is my total pressure to give me the partial pressure of the air. And when there is no iodine, this is the partial pressure of my iodine taken from the total pressure. So this is the partial pressure of the air at the two different locations, or I guess times. If you plug those into a calculator, I came up with 0.982 atmospheres, or if you were working with millimeters of mercury and want to check your answer, 746.5 millimeters of mercury. Now I'm going to use that up here. So use the same units for these two pressures. This becomes my answer from a moment before for Kc prime. I can say 747 is my total pressure in millimeters of mercury. My partial pressure log mean for the B component. And the temperature is 313 Kelvin, and R is 82.06. Atmosphere, centimeter cube, mole, K. I'm sorry, that's a little hard to read. I understand. It's okay to be using atmospheres with this because those millimeters of mercury are going to be canceling out. Will be 2.64 times 10 to the minus fifth, and the units are moles per centimeter squared atmosphere second. That's my final answer. So that's K sub G. We have one last step in this problem. Final answer. and that is to figure out what is the molar flux. Now we're going to do this assuming unimolecular diffusion. Take a moment based on that. What do you come up with as an answer? All right, so doing this, N sub A is going to be kg times the partial pressure of A at the surface minus the partial pressure of A in the free stream. And that is going to be 2.64 times 10 to the minus 5th. My partial pressures, again, this is for component A, which is the iodine, 1.03 over 760 minus 0. The units on this were moles per centimeter squared, atmospheres, seconds. This is atmospheres. So my flux will be 3.57 times 10 to the minus 8 moles per centimeter square per second. All right, so that concludes this problem. Be sure that you are seeing how maybe you could have done all those steps, because when you work a homework problem from the book or my assignment, they're not going to break it down into all those tiny steps. So this guided you through the necessary pieces, but make sure that you understand why I might have chosen to do it in that order. All right, so I will see you guys back in class next Wednesday, and we'll be looking at some other examples. Thank you very much for your time. Answer